Over the last few centuries, the achievements of the human race have reached dizzying heights. Not only have we travelled to space, but our science and technology have helped us to control the Earth below. But that control has come at a price. 2 centuries after the Industrial Revolution, the Earth and its vital atmosphere is breaking down under the collective weight of modern pollution. Now, the very science which gave us control is predicting the extent of our environmental destruction. Its name has already gone into our language.
The greenhouse effect is neither brand new nor is it controversial. It's probably the best accepted theory in the atmospheric sciences.
There's no doubt that the concentration of greenhouse gases is increasing and that our climate's changing, and we've got to do something about it.
It means we're going to place the planet into a position where it's warmer than it has been for hundreds of thousands of years. So the climate patterns are going to be different from what they've ever been in human experience.
There is no phenomenon which will cause humankind to change in the way that this phenomenon will, and undoubtedly will.
I think we've got to act on the basis that on the balance of probabilities that warming will continue and that it will have a serious impact.
Hello and welcome to Quantum. Tonight we're devoting the whole program to the greenhouse effect, and as you've already heard, it's serious. That's why, starting tomorrow, people will gather in 10 cities around Australia for Greenhouse 88, a conference organised by the CSIRO and the Commission for the Future. Greenhouse 88 will bring scientists, business leaders and politicians together for 3 days' intensive consideration of our global future. Over the next half hour, we'll be looking at what we've done to produce the greenhouse effect and what we can do to stop it. But first, Jeff Birchfield looks at what scientists mean by the greenhouse effect.
For scientists, Antarctica is a storehouse of information. Deep within the ice is a record of our planet's most precious asset, the air. Drilling out a core of ice is like looking back across thousands of years. Trapped in its layers are small bubbles, an uncontaminated history of the atmosphere, revealing what it was once like and how much it's altered over the years. Since the 50s, we've kept much more detailed records of change. Not just the air we breathe, but the upper atmosphere as well. Those records reveal the components in our atmospheric system that for millions of years have permitted life on the planet to flourish. Far from being just a lifeless mass of air, our atmosphere is actually a dynamic machine, complete with its own natural checks and balances. A system of invisible mechanisms. One of those mechanisms is the carbon dioxide cycle. I'm standing in it. In fact, I'm part of it. I breathe out. Plants store it and use it up. But CO2 has another function. After the sun's radiation has streamed down through our atmosphere to heat the world, the warmed Earth gives off its heat in the form of infrared radiation. If it wasn't for the CO2 in the air, this whole process would make the Earth a most unpleasant place to live. Instead of all this infrared heat escaping back into space, the carbon dioxide in the atmosphere absorbs some of it. Like a blanket, it moderates the overall temperatures that we enjoy and need to survive. If this didn't happen, we'd freeze. But you can have too much of a good thing. A high level of CO2 would have the opposite effect. Temperatures would soar to extremes and we'd all bake. A greenhouse out of control. It's a delicate balance. Since the beginning of the Industrial Revolution, we've increasingly devoured fossil fuels like oil and coal. But burning these fuels is quickly releasing massive reserves of CO2 that have taken millions of years to accumulate. Can nature cope with such a sudden change? Or are there already signs of an imbalance, heralding dramatic shifts in the Earth's climate? Using the air bubbles locked in Antarctic ice to look back across the centuries, scientists are beginning to get an answer. For 160,000 years, the levels of carbon dioxide have only fluctuated slightly. But the melted ice from the time of the Industrial Revolution shows that since then, the amounts of CO2 in our air have soared. Modern agricultural practices haven't helped either. To meet the world's rapidly expanding human population, intensive farming has increased the levels of other gases which could compound the greenhouse effect. The most prominent of these gases are nitrous oxide and methane, which has risen 160% in the last century. If climatic records show an observable rise in the Earth's temperature, then it might indicate a connection with those greenhouse gases.
In fact, temperatures have been rising in the past century. Admittedly, only a degree or so until recently. But in the 80s, things have really heated up. In just 8 years, the world record for highest temperature has been shattered 4 times. And this summer is shaping up to make it 5. Maybe they're just natural fluctuations, although the rate of increase has scientists worried. They see retreating glaciers and unusual weather patterns as confirmation of a global imbalance, the rumblings of a massive change of our own making.
I don't know about you, but I feel hot. It's 35 degrees here in Sydney at the moment. That's 6 above the average, and according to the Weather Bureau, this weekend is going to be another stinker.
On a day like this, how could you possibly think there's anything wrong with the weather? After all, living in Australia, we've become accustomed to warm seas and a blazing sun. And if the forecasts are correct, we can expect a lot more summer in the future, perhaps more than we need. The media has been full of dire greenhouse forecasts, of agricultural heartlands turning to dust bowls and salt pans, houses and whole nations being washed away, and frequent bushfires. And while these are likely outcomes, forecasting such global calamities is not a simple business. All these predictions are the electronic guesswork of massive computer programs instructed to model the complicated circulation patterns of our oceans and atmosphere. And every day, those models are getting better. This is the headquarters of Australia's greenhouse research effort, the CSIRO Division of Atmospheric Research, and latest computer climates generated here and around the world are forecasting big upheavals. In 40 years, we'll probably have doubled the concentration of greenhouse gases in the atmosphere, and that will raise the average temperature as much as 4 degrees Celsius. While that might sound quite pleasant, the thermometer won't climb evenly around the globe. Warming will be most dramatic towards the poles, where winter temperatures may rocket 12 degrees. And these are only average temperatures. Extremes will be much greater. If it wasn't for the oceans, things would be getting hotter a lot quicker. The oceans have an enormous capacity to absorb heat. Enough capacity, in fact, to disguise the severity of atmospheric warming for several decades. But as the oceans warm up, the water in them expands, and that means a rising tide line. In fact, sea levels have already risen by 10 centimetres in the last century. And if the warming continues beyond next century, the polar ice sheets will start to melt as well. In 40 years, the sea level will probably be a metre higher. Not a huge amount perhaps, but enough to make its presence felt. Where I'm standing now would be underwater in a high tide. Plants and animals like those white tube worms down there will notice it first. Animals like these that have a strict preference for a particular tidal height will have to move up to match the sea level rise. It's such early warning signs that geographer Eric Bird is expecting soon.
Well, in the built-up areas of coastal Australia, where, of course, more than 2/3 of Australians live, we're going to have some problems, especially in low-lying areas where some of the development is very close to present high tide level. We've already got beach erosion on quite a large scale. It'll get much worse. We'll have erosion of salt marshes and mangrove swamps, and a tendency for the salt marsh and mangrove swamp to migrate landward where it can. If there's agricultural land, it won't be able to. And so probably we'll have a lot less tidal wetland as the sea level rises.
And while inundation is the most obvious consequence of warmer oceans, cyclones are the hidden surprise. When the warm waters extend southwards, so too will the storms. It's a very real possibility that cyclones will wreak havoc as far south as Brisbane and perhaps even Sydney. But in between the cyclones, we can expect ordinary rainfall to increase too, about 10% around the globe. Here in Australia, that extra rain may actually bring about one of the greenhouse effect's few positive changes. The additional water, especially when combined with the extra carbon dioxide in the atmosphere, could be a growth-inducing bonus for the country's often drought-ridden vegetation. Roger Gifford has been studying the possible impacts on Australian native plants.
Carbon dioxide is in fact a kind of fertilizer for plants. It promotes plant growth. So alongside the greenhouse effect, which is a warming of the globe, we have a carbon dioxide fertilizing effect, which is stimulating plants and crop yield.
But it seems it all depends on the other nutrients which are available. Without enough of them, the increased CO2 and rainfall may be more of a hindrance than a help, as Snow Barlow found in his study of commercial pine trees.
They grow 20 to 30% faster at a doubling of the CO2 concentration. That's fine, provided they have all the nutrients that they require in abundant quantities. That's not the reality of Australia. Australia is a fairly poor nutrient soils, and therefore phosphorus deficiency is sort of endemic. And when you grow plants at high CO2, at low phosphorus, often they grow worse than they do at low CO2 because they try to grow too fast for the available phosphorus resources and indeed just tire themselves out and die.
Both scientists agree that along with the increased heat and humidity will come pests and diseases, which may limit any benefits provided by extra plant growth. Whatever happens, we'll have to readjust our agricultural practices to a different climate. Of course, a rising temperature means a rising snow line. Every degree of temperature increase will push the snow line 100 metres higher. And for many of Australia's alpine areas, there's not that much mountain left. Snow will only be guaranteed on the tallest peaks, and even there, the season will be shortened. There'll be less meltwater for the dams, and the winter ski industry will face a barren future. And while all of that will be an irritation for Australia's skiers, the effects could be much more devastating for the animal and plant life of these regions, because for them, there's nowhere else to go. Pushed by the endless demands of population and agriculture, wildlife around the globe has been forced into isolated pockets of land, trapped, in fact, on islands in a sea of humanity. Once the climate shifts, these areas may no longer support their wildlife. Whole ecosystems will be left high and dry. It's the wildlife that is so often left out of our equations. What the greenhouse scenario is telling us is that we don't exist in isolation from the other forms of life on Earth. We need them more than they need us.
If carbon dioxide is our big problem with greenhouse, then we've got to understand the carbon cycle if we're ever going to get the scales back in balance. This coastline is as good a place as any to start because it's full of carbon in the plants, the air, the ocean. There's a fixed amount of carbon on Earth, but it moves in a slow cycle, constantly changing its form. Take the carbon dioxide molecules floating about this stretch of coast. On average, they've been in the air here for about 1 year. So while they're in Australia now, a year ago they would have been pumped into the atmosphere anywhere in the world.
But that was a year ago. And any minute now, these carbon dioxide molecules could be sucked back out of the air by one of the trees around here. And if the local trees don't get them, then the tiny single-celled plants called phytoplankton, which live out there in the ocean, certainly will.
The ocean absorbs carbon dioxide as a gas from the air. Phytoplankton in the water take up the dissolved gas and turn it into solid carbon in their bodies. Once here, the carbon enters the food chain and eventually settles to the ocean bottom in a steady rain of dead bodies. The thick layers of carbon that accumulate down here are locked away for the millions of years that it takes the seafloor to drift slowly sideways towards the volcanoes, where the whole cycle starts over again. The other big carbon pumps, and the ones we have more control over, are of course the forests. Trees stabilise the Earth's climate, and as far as greenhouse is concerned, their role is crucial. As trees like this grow, they use photosynthesis to pull massive quantities of carbon from the air and put it here into the solid mass of timber and leaves. So this eucalyptus tree is in fact a giant storage container of carbon. The forests then are vast carbon factories, with each tree pumping carbon gas in and stockpiling solid carbon away. Clearly, the more trees there are, the more carbon that can be locked up. But the reverse is also true, and that's where all our greenhouse problems are being made far worse. As soon as we learnt how, humanity started pulling trees down, and ever since, we've been clearing trees and bushland at an unprecedented rate. Every tree that's been felled is one less carbon pump cleaning the air and one more lump of carbon sent back into the atmosphere.
We've got to stop destroying native bush in all its manifestations across the world. Stop chopping down tropical rainforests, stop draining marshlands, stop destroying mangrove swamps, etc., etc. And then start replanting. Get the carbon dioxide pumps working and put the right trees back in the right place. So that means replant the rainforest, replant with eucalypts here in Australia. Don't put stupid things like pine trees in. I know they grow fast, but they are northern hemisphere temperate trees.
The scale of replanting that's needed is massive. Rough estimates suggest that if we replanted an area the size of Australia, we could soak up the 5 billion tonnes of carbon dioxide we release every year. It'll take a global commitment to start replanting, and all it will do is buy us time.
But that's not the end of the carbon dioxide story. Remember the oceans and how they actually process most of the carbon dioxide out of our atmosphere with the phytoplankton. Well, just because these single-celled plants are underwater is no guarantee of protection.
Phytoplankton, like all other life forms, are very sensitive to ultraviolet radiation. They're protected from it by the layer of ozone gas in the upper atmosphere. This protection is being seriously threatened by human activity. Man-made gases, the infamous chlorofluorocarbons, which are common in spray cans, are reaching the upper atmosphere. There, they react chemically to destroy ozone molecules. Though a separate problem, a thin ozone layer is set to compound the greenhouse effect, because damage to the ozone layer will allow ultraviolet light to stunt and destroy the phytoplankton.
Just how much damage would be done depends on many factors. However, a serious worsening of the ozone layer would almost certainly have a major impact on the world's biggest system for processing carbon dioxide. With that comes a considerable worsening of the greenhouse effect.
One of the hallmarks of the modern world is our overwhelming dependence on energy. Most of us take it for granted that it's our right to expend energy at the flick of a switch or the turn of a key. But that's something that's going to have to change. Because most of our energy comes from burning fossil fuels like coal, oil and gas, which add to the greenhouse effect by releasing carbon dioxide. Of all the fossil fuels, coal is the worst. Each tonne of coal that we burn produces 3 tonnes of carbon dioxide. That's twice as much as natural gas and 30% more than oil.
Here in Australia, that presents us with a real dilemma, because 82% of our electricity comes from coal. Not only that, coal is one of our major export earners as well. That means any decision to replace coal with something else is a tough one. But faced with the inevitable, that's something we may well have to do.
For many, the natural alternative is nuclear energy. As far as greenhouse gases go, it has a clean bill of health. But we could just be exchanging one environmental hazard for another. To match the output of Australia's coal-fired power stations, we would need 28 nuclear reactors of the most common type, the American light water reactor used at 3 Mile Island.
At the moment, Australia doesn't have any nuclear power stations, and so far it's government policy not to build any. But if that were to change, a major consideration would have to be, what do we do with the radioactive waste from 28 nuclear reactors? Solar energy is something that's been embraced warmly by many Australians, but it still tends to be used only on a domestic scale, despite the fact that Australian research is currently demonstrating that solar power has larger scale applications as well.
Campbelltown Hospital in New South Wales is trialling solar energy to provide steam for sterilisation and hot water. And in the outback, White Cliffs, near Broken Hill, has been drawing its power from a solar array since 1984. This Australian National University project has proved solar power can be cost competitive with a diesel-powered generator. Next year, an improved solar collector is expected to deliver energy at a fifth of the cost of diesel. Ultimately, project leader Professor Stephen Kenneth is confident that solar energy will be able to compete with fossil fuels.
It's certainly possible for solar energy to meet all of our energy needs if we really put our minds to it and put our efforts to it. There's no single form of energy that I can think of that can't be satisfied by solar energy, and that's not to say that one has to do that immediately. One would imagine over many years one could develop those energy forms.
Professor Kenneth points out that the installation and electricity generating costs of solar systems have dropped to a tenth of what they were a decade ago.
But whatever solution we choose to reduce our demand for coal-fired power, really that's only part of the answer. Because electricity provides less than 14% of our total energy needs. By far our biggest energy demand is for petroleum products.
In fact, just over half of all the energy we consume comes from oil. At the heart of every industrialised nation is a transportation system. Trucks, ships and planes are all fuel hungry, and petrol is cheap. Yet oil is a limited resource. At the rate we're using it now, current reserves will run out in 50 years' time.
At the moment, we don't really value energy as a resource very highly. If you think about petrol, for example, apart from water, there's no liquid we can buy in bulk that's cheaper. We pay more per litre for milk, for beer, for orange juice, for cask wine. All of these liquids we value as more precious than oil, even though they're liquids that we can produce without limit. And oil is nature's one-off resource that we're using very rapidly.
According to Professor Lowe, we're going to have to rethink our attitudes towards transport. In the long term, we may be forced to use fewer cars because of a shortage of fuel. In the short term, we should be putting more emphasis on public transport. A full bus, for example, is 20 times more fuel efficient than a car. And certainly one way people can make an individual contribution to slowing down the greenhouse effect is to cut back on private vehicle usage.
Basically, there's no quick fix solution to the greenhouse problem. There's no magic technology out there waiting to come to the rescue. Although superconductivity could certainly help reduce our energy consumption, it's still a long way off being realised. And in the meantime, many scientists are saying that we have to start acting now. That means we have to change our ways now and start doing things like, for example, designing and constructing energy-efficient buildings like this one here in Sydney, called Grosvenor Place.
Using a combination of solar power for domestic hot water and a radically innovative design, this building operates without any boilers whatsoever. It freezes water overnight for the following day's air conditioning needs and recycles the heat generated by the refrigeration units for any heating requirements.
What date are we on?
Heat is collected and recycled throughout the building from many other sources, including the light fittings. Special reflectors enhance the light, reduce the number of bulbs needed, and cut lighting costs by half. The windows are double glazed to prevent unwanted heat going out in winter and coming in summer. Sun shields, carefully angled to allow for changes in the sun's position throughout the day, regulate the amount of sun entering the building.
All that's very impressive, but one building on its own won't have much impact on our energy consumption. We have to think on the scale of whole cities. In Japan, they're already designing a major city that will use less than a third of the energy of a contemporary city of the same size. But perhaps the most crucial message to remember about the greenhouse effect is that it does link us all together, wherever we live in the world. What we do as individuals to cut back on greenhouse gases and ozone-damaging CFCs is important, but it's what we do as a global community that'll really count.
It's also important to realise that because the climate changes are going to be regional, those effects that occur in the US or in Europe will be quite different to those that occur here. The US and Europe are not going to research what happens for Australia. We'll have to do it ourselves.
It's now becoming such a worldwide issue, with so many people in the street knowing about it, let alone in the upper echelons of government, that my task will be made much easier by public pressure. The whole world is going to want to know about the greenhouse effect and how it will affect them.
If we can nickel and dime this problem, if we can do a little bit here and a little bit there, pretty soon we might cut it in half. And if we get the 2-degree warming period not at 2010 or 2020, but at 2050, then that does a lot, because the rate of change is what causes damage. The faster things are, the less we can adapt, the more damage to us. The faster things are, the less tree species or other natural habitats can adapt to.
Most people I know want their children and their grandchildren to have as good a life as they've had. And I think if there is global agreement, as there has been on the ozone layer, then we could perhaps, for the first time in our lifetime, the first time in human civilization, see a genuine global determination to do something about caring for the Earth.
That's Quantum for this week. Next week, Andrew Waterworth goes to the USA in search of the origins of the universe. Exploding the Big Bang Theory. Just one story on Quantum next week. I hope you'll join us. Until then, good night.
In just a few moments on ABC, our Wednesday special, a re-screening of Inundation of a Nation. Paul Barry's report on the recent massive floods in Bangladesh, one that shows the scale and human face of this disaster. Our ABC special, right after a news update.